Hi, Dr. Smith. This is Rizwan, the first Muhammad uh, in the class. So today I'm going to present my final presentation of data mining 2 course on alternative fuels of buses to enhance mobility in Central Florida. So the background of this project is that the University of Central Florida is one of the largest university by student enrollment in the nation. It took the initiative to become climate neutral by 2050 and has another target to reduce carbon emission by 42% by the year 2030. Even though the money is tight here, UCF is teaming up with the shuttle company to use alternative fuels, which are the better for environment. So, but getting around in Central Florida, especially on UCF campus, is challenging. It costs a lot to keep the buses running because they have to travel long distance and break down frequently. And not many people are riding the bus. That is another issue. So UCF knows that using cleaner transportation is important for the environment and for people. Electric buses are great because they don't cause pollution and need less fixing, but they can only go far with needing to charge up. So UCF is working with, partnered with Lynx and the city of Orlando to figure out which buses are the best. As part of the project team, we are now working with diesel, CNG, propane, and electric buses on different routes around the campus and in the city. The ongoing project aimed at evaluating the alternative fuel bus technologies and their infrastructure has already completed, we already completed one season of data collection, which is winter. However, the further data collection is required to comprehensively assess the various aspects of the alternative fuel. Uh, um, like Despite the ongoing nature of the project, the existing data presents an exciting opportunity for data mining, offering the potential for engaging class projects to analyze and derive insights from the collected data. This initiative not only underscored the University of Central Florida's commitment to environmental stewardship and innovation, but also inspires a greener, more resilient transition infrastructure aligned with national sustainability objectives. Uh, the motivation for this project is UCF recognizes the importance of using cleaner transportation for both the environment and the people. Despite financial constraints, UCF is committed to finding sustainable solutions to transportation challenges, such as high cost and frequent breakdowns. Then optimizing these issues and devising new strategies is the main concern for us, who we are doing this project. The project is beneficial because it aims to evaluate alternative fuel bus technologies such as the uh, propane, CNG, and electric to find the best option for improving transportation efficiency and reducing environmental impact. By collecting and analyzing data on the performance of these buses, the project team will inform decision making to create a greener and more resilient transit infrastructure. So these are the methodology and the steps that we have implemented in our data collection process and that I followed in this presentation and the project. So first one is procurement of telematics device. So then we go for data collection. After when we have the devices, then we go for data collection. And after collecting the data, we use three different types of devices. We gathered the data in one single Excel sheet in one platform. After that, we do the data processing, pre-processing. Then we do the most important phase, feature selection. We targeted the required features, like the features we need to work with, and the other features we just keep them aside. Then we do the modeling and data exploring, and then after that we go for comparison of experimental results. So Here, I can show you the buses. These are the buses that we have tested. The first one is this is at UCF campus. Uh, these are in UCF downtown campus, and this is also in UCF campus. This is CNG bus. This is electric bus. This is uh, propane bus, and this is diesel bus. So since the project is evaluating the energy of all the buses, but we have completed the data collection only for the electric buses. So in here I'm just focusing on electric buses. And also we have started the data collection for the other types of buses, but for the analysis and data mining, like plots, I have also sometimes used that data so that we can find some insights from them. So since I mentioned that we have three types of telematics device, first one is called motive, and this one is the motive, like, and this one is the Q Starch device. This is a GPS device. This is very high accuracy, like the sports cars, they use this type of devices. And this GPS device, it doesn't need any kind of connection. It's wherever we put it, it is giving us the signal from that coordinate. And for this motive device, we need to plug it in the OBD port, on board diagnostic port. This port looks like this, and this is for the diesel buses. The port is right here. So we collected, and when we see the two green signal, that means my connection is okay and it's ready for data collection. And this is the interface of the motive, that how we get the data. This is like how, like this is a map of the bus, the trajectory it shows, and it shows like where it is, basically like a version of Google Map. It's that way too easy to understand. Okay, and this is our route. So this is UCF main campus, and this is UCF downtown campus. So all our routes are UCF main campus to downtown campus, all the way to 417 and 408. And here also we have some stops, like they are, we call it interrupted flow. And when we are in the 417 and 408, we call it the uninterrupted flow. So the reason for that is we need to understand the behavior of fuel consumption in this interrupted and uninterrupted flow. So in that way, we can decide like how much like energy is consumed and how much energy is idled in the intersection or in the traffic. Okay, so uh, next, these are the parameters that I work with, and I get it from which platform. So based on the data, we get most of the data from Vericity. So Vericity is developed by ChargePoint, a company, and they install these devices only in the electric buses. So we don't need to use Modif on electric buses. So yeah, we can see we get all the data from Vericity, and we have some data from Motive, and QStars is also giving us some data. So for data analysis and visualization, R has been used, and I have started with the clustering, partitioning, and hierarchical clustering. So these results are from k-means clustering applied to the dataset. Before clustering, the data was scaled to have zero mean and unit variance. So each row represents a cluster center showing the mean value of the variable in each cluster. For example, cluster 1 is characterized by low values in all variables. Cluster 2 is moderate to high values in all variables, and cluster 3 is similar to cluster 2, but with some differences in variables like time charging and number of charging sessions. These are two parameters from my dataset. So each data point is assigned to one of the clusters based on the proximity to the cluster center. In the output, each data point is labeled with the cluster to which it belongs. So this is principal component 1 and principal component 2. Then we have cusp plot, and we have clustering like this way, and we have elbow method, number of clusters. Because the another thing, the comparison between 2 and 3 clusters, this is 3 cluster and this is 4 cluster. The difference is the running k-means with different number of cluster provides insights into how the data behaves under different assumptions. Adding more cluster allows to finer distinctions, but can also lead to overfitting if the cluster becomes too specific, or if there isn't enough data to support the additional cluster. The elbow method helps identify the appropriate number of clusters by looking for a point on the plot where the rate of decreases is in WSS slows down, forming an elbow. This point suggests the optimal number of clusters to use in the K-means algorithm. So next, we have silhouette method is another approach to evaluate clustering quality, where higher silhouette widths indicate better defined clusters. The optimal number of clusters can be identified by selecting the value of K that maximizes the average silhouette width. So then we have the visualization of the distance matrix as a heat map, and then applies the Clara algorithm package for visualizing the resulting clustering. Then I did the dimension reduction. Dimension reduction has been performed using principal component 1 and principal component 2, visualizing using the factor extra package. And then after removing the duplicate rows from the data, oh yeah, and this is a script plot. And after removing the duplicate rows from the data, t-distributed stochastic neighbor is performed. Colors are defined based on the target variables, and the t-SNE results are plotted. Then the result, the analysis calculates the Bayesian network model, Bayesian information criteria scores for different combinations of algorithms and methods. It creates a matrix to store the BIC score, iterates over each algorithm and method to calculate the BIC score using the score function, and then sorts and prints the resulting matrix. Lastly, the analysis defines a function bootstrap to perform bootstrapping on the data, sets the number of bootstraps to 100, sets a seed for reproducibility, creates a cluster object for parallel processing, exports necessary objects to the cluster, performs bootstrapping using Parlaply, and plots a Bayesian network model from one of the bootstrap samples. So yeah, so now I do a temporal analysis between my two factors. One is speed and another is fuel consumption that we get from the data. And this is a temporal analysis. So this has been done in the morning. So we call it the AM peak, and this has been done in the afternoon. We call it PM peak. So as you can see, with the increase of the speed, the fuel consumption increases. But after certain time, when the speed is uniform, fuel consumption also behaves like uniform in both cases. So this is for diesel buses and this is for propane buses. Propane is one kind of gas, and propane is the commercial name, and the scientific name is LPG, liquefied petroleum gas. And they're also behaving the same way. With the increase of the speed, and their fuel consumption will increase. So this is for AM peak and this is for the PM peak. So now we have a plot for CNG, compressed natural gas. So we have the similar type of graph, like with the increase of speed, we have the increase of the fuel consumption. For electric buses, they use the battery as their fuel. So the unit for battery is energy. The energy distribution is like this. So as you can see, uh, we don't have the speed profile yet, but this is like the energy consumption, and it's very similar like how they like whenever we start the bus, it starts to consume energy. And let's move on. And we did a model based on that, like the prediction model underwent testing with various machine learning algorithms, and this in-swing table presents a comparative analysis of these models, including their respective predicted mean square error and R-square error values. Based on the MEC and R-squared values, uh, we can see the random forest is the best of the choice as it has the lowest MEC and high R-squared values, indicating better predictive performance compared to the other models. So Here, this figure illustrates the actual data points depicting the relationship between SOC used driving and energy driven in kilowatt. And it marks an estimated SOC used driving value for a specific energy driven value. So from the model and the figure, we can see the slope of the curve, which is approximately 3.45, something like that, indicates the change in the SOC driving, SOC used driving for 1 unit change in the SOC used driving percentage. It means that uh, according to this model, it means that if the energy driven value is 5, it suggests that SOC used driving is expected to be approximately 1.417. And at the same way, for SOC used idling, the energy idle value for the used energy of 5 kilowatt, the, the energy idle value is 1.56. So from here, we can understand that energy idling is consuming more battery percentage. So SOC is basically state of charge idling, charge driving. So we can compare SOC with an example of our phone's battery. Like the battery is 100% and then it's decreasing. So SOC used driving is the state of charge depleting when it's driving, and SOC used idling means SOC is decreasing when it's in idling, it's not moving. So from this graph, we can see the energy is depleting more in the idling. So this is a big concern. Like if I spend most of my energy in idling, then how am I get a good performance? Because bus will run most is its operation time. So if it's use more energy in its idling time, I mean its non-operation time, then it's a scary thing in the transportation sector. Okay, so yeah, then we go for the final prediction model. And in the final prediction model, predicting SOC model data for different buses. So we wanted to know which bus perform how. Like this is for the whole fleet. Like we cannot tell which bus is the best and which bus is the worst from this data. Like this is a baseline for us. So from here, a distinct pattern emerged regarding the SOC driving and SOC idling. For instance, buses with numbers 290, 291 exhibit relatively higher SOC idling values than their SOC driving counterparts, indicating that they tend to use more energy while idling than while they're in motion. Conversely, buses number 292, 294, 296, 297. They showcase a notably disparity with significant lower SOC idling and SOC driving values. This suggests that these buses conserve more energy during idling periods. Such insights into SOC variations across different buses can inform strategy for optimizing energy usage and improving overall efficiency in the fleet management. So then we can say the bus number 290 exhibit relatively higher SOC values for both driving and idling, and according to that, it performs the worst in the fleet. And buses number 297, they exhibit the lowest SOC driving and kind of like lowest SOC idling, and they're the best performing buses. So yeah, like we can we can predict which one of my bus is good and which bus is bad. It's very important for us. So yeah. So here comes the conclusion. So from the conclusion, we can have insights from this predictive analysis that the valuable insights into the efficiency and performance of individual buses have been gleaned through predictive analysis of energy use patterns within the fleet. Then we have the deeper understanding of state of charge variations during driving and idling scenarios across different bus numbers. Then we can say the energy efficiency. We can find the efficient bus and we can find the non-efficient bus, and it will give us the uh, idea to go for strategic deployment of better performing buses, such as bus number 297 for long range routes can optimize energy usage where charging infrastructure is limited. So buses with lower energy efficiency like 290 may require closer monitoring and maintenance requirement considerations to ensure for optimal performance and reliability. So yeah, so these are the things we can conclude from our analysis. So thank you, Dr. Smith. I know there is no option for asking questions and answering. So yeah, thank you so much. I'd like to thank you so much for teaching me a lot of methods of data mining. I did data mining one, and this is my data mining two. So yeah, I can feel that I didn't I had zero knowledge of machine learning, and I mean R visualizations, but now I feel good about it. Like I can do at least something. So thank you so much, and yeah, that's all from me. Thank you.